Dear students, we have to see some more additional points about coefficient of determination. In the two variable model, we have stated that r square is the square of r, and in the multiple linear regression model, r square is the square of capital letter R, the square of correlation coefficient, the square of multiple coefficient of correlation. Now let us see why this is known as the square of the correlation coefficient. Now let us see what is actually it is a correlation between actual y and estimated y. It is a correlation between actual y and estimated y. That is why it is known as correlation and its square. Let us see. Let r square between actual y and estimated y is sigma of yi minus y bar, y hat minus y bar, the whole square. In the case of it is y hat bar, but we have proved earlier that it is nothing but y bar. Y hat bar is equal to y bar. So I write it as y bar instead of y hat bar. Correlation is sigma y minus y bar into y hat minus y bar, its square, divided by sigma of yi minus y bar square into sigma y hat I minus y bar square. That is root of sigma yi minus y bar square, root of sigma y hat minus y bar square, which we write as sigma yi y hat I the whole square divided by sigma yi square into sigma y hat I square, sigma yi square into sigma y hat I square. Now consider the numerator sigma yi y hat I. This sigma yi y hat I, sigma yi y hat I can be written as equal to sigma, this yi is y hat I plus u hat I into y hat I. Sigma yi y hat I is sigma y hat I plus u hat I into y hat I. This is equal to sigma y hat I square plus sigma u hat I y hat I, and sigma u hat I y hat I is 0. So this is equal to sigma y hat I square. That is sigma yi y hat I is equal to sigma y hat I square. Now r square is equal to sigma y hat I square all square, because there is a square here, divided by sigma yi square into sigma y hat I square. As you know, one term here and one term here cancels, equal to sigma y hat I square by sigma yi square. This we have written as ESS by TSS. So what is r square? R square is the square of the correlation between y and y hat. That is why the name R square, because it is nothing but the square of the correlation between y and y hat, even though the interpretation is different. The interpretation of R is a measure of linear association between variables, whereas R square is the percentage or the proportion of the variation in y explained by variation in x. But as it is a measure of correlation between y and y hat, this quantity can also be interpreted as if R square is small, we can say that very small variation in y is captured by y hat, the sample regression line. If R square is small, we can say that only a small variation in y is captured by y hat or the sample regression line. So remember this point always. R is nothing but the correlation. R square, because R square is nothing but the square of the correlation between y and y hat, because this quantity is nothing but the square of the correlation between y and y hat. A small R square, capital letter or small letter, in some textbooks no distinction is made between capital letter R square or small letter R square. Anyway, a small R square means only a low percentage of the variation in y is captured by a variation in y hat or sample regression line. Now, given this interpretation of R square, let us see how we compare two R square values. How we compare two models based on R square. To compare two R square values, three things must be considered. One, n must be same. N must be same. Both models should be based on same sample size. Second, y must be same. Y must be same. X can have any form, any number. So if you want to compare two models based on R square, you must ensure that sample size is same. You must also ensure that y is same. But x can have any number. For example, consider a model yi summum beta 1 plus beta 2 x2y plus beta 3 x3y plus uy. ln yi summum beta 1 plus beta 2 x2y plus beta 3 x3y plus uy. Even if these models are based on same sample size, same number of explanatory variables, you cannot compare these models based on R square, because the dependent variable is different. In the first case, R square measures the proportion of the variation in y explained by x. That is, in the first case, R square measures the proportion of the variation in y. But in the second case, variation in y is delta y by y. And delta y is not the same as delta y by y. Both are different. So variation in y, change in y, is not equal to change in ln y. Change in y is delta y. Change in ln y is delta y by y. So comparison is not possible. Now the question is, how do we compare two models with different explanatory variables? Let us see an example to see how we can compare two models based on R square. Now, suppose that we have a relationship between consumption of coffee, quantity demanded of coffee Y per person, and the price of coffee X price. And applying OLS, Y hat I is equal to 2.69 minus 0.47 XI, and R square is equal to 0.6628. That is in terms of Y and X. R square is 0.6628. That is 66% of the variation in coffee consumption is explained by variation in price. Now suppose that I convert this into L and Y. L and YI summum 0.77 minus 0.25 L and XI, and R square is 0.7448. Now the interpretation is, if there is a 1% increase in the price of coffee, there is a 0.25% decrease in the consumption of coffee. So consider R square in this model. It is 0.66. In this model, it is 0.74. But R square in these models cannot be directly compared. But if you want to compare R square in these models, the procedure is like this. And the procedure is, consider this model, you will get ln y hat. Take anti-log of this, you will get y hat. Estimate this model also, obtain ln y hat, take its anti-log, you will get y hat I. Then calculate R square between sigma yi y hat I square by sigma yi square into sigma y hat I square. That is, estimate both the models, obtain ln y hat, then take its anti-log, then calculate this R square. The R square we have just derived. The R square we have just derived. And if this R square is directly comparable with this R square. And using this formula, the R square obtained is 0.71. Again, this is a little more than this. So we may say that the second model is better than the first model in terms of R square. So remember this, coefficient of determination is nothing but the square of R square. Square of R square means it is the square of the correlation between yi and y hat I. Now, a question that is often asked in the context of econometrics is, what is the role of R square in econometrics, in empirical research? Actually, R square is not a very important quantity in econometrics. Some researchers play the dangerous game of maximizing R square. And many econometricians say that this practice is dangerous, not desirable, not generally promoted. The reason suggested by them is that in econometrics, our concern is not R square, our concern is one, coefficients. Second, the sign of the coefficients. Third, significance of the coefficients. These are the three things which we consider first. After estimating a model, we will consider the magnitudes of the coefficients. That is, the strength of association obtained from the magnitude of the coefficients. Then we will consider the sign, whether the sign of the coefficients is in accordance with our expectations. Then we will consider whether it is significant using the t-test or Z test. If the model is okay with respect to coefficients, their sign and significance, then we will accept this model, whether R square is high or R square is low. R square is high or R square is low. Suppose that the coefficients are not very big, the sign is not in accordance with our expectations, then even if R square is very high, it is not a useful model. On the other hand, if all these are satisfactory, if R square is low, that does not mean that the model is not good. So as one author, Goldberger, says, R square has only a limited role in econometrics as a measure of goodness of fit, or as a measure of how fit is the sample regression line to the sample data. A high R square is not in favor of the model, or a low R square is not against, or is not evidence against the model. Our concern is the coefficients, the sign of the coefficients, and their significance. In this, if R square is good, is high, it is well and good. If R square is low, it does not mean that the model is not good. Remember this always in your mind. R square is nothing but how fit is the sample regression line to the sample data, or it is a measure of the correlation between y hat and y, a measure of correlation between y hat and y. Y hat points lying on the sample regression line, y is the entire spread. If most of the observations are close to the sample regression line, R square will be high, otherwise it will be low. So it has only a limited role. Our concern is not to explain how fit is sample regression line to the sample data. Our concern is how to use the sample data and estimators generated from the data to make inferences about parameters, that is, the coefficients, the sign, and the significance. Even if R square is low in a model, it is not evidence against the model. Even if R square is high, that does not mean that the model is necessarily good. So keep this point always in mind. R square has only a very limited role in econometrics as a measure of the desirability of the model, the fit of the model, the goodness of the model, etc. Then let me say one more point about R square. Not about R square, but about R bar square. Now, when you introduce an additional variable in the model, R bar square will increase if and only if the value of t is greater than 1 in absolute value. In absolute value. That is, you introduce one more explanatory variable in the model, then R bar square will increase if and only if the absolute value of t of the coefficient of the additional variable is greater than 1 in absolute value. Similarly, if you are introducing a group of variables, R bar square will increase if and only if the value of f is greater than 1. If you introduce a group of variables, then R bar square will increase if and only if the value of f is greater than 1. These 2 points should be kept in mind. Then let me conclude this by considering a few problems with the R square in general. A few problems with the R square in general. Now, let us see what are these problems. I discussed this very quickly. One is the problem of spurious regression. The problem of spurious regression. The point is, even if two variables are not related, due to spurious correlation or spurious regression, you may get a very high correlation, a point which was originally introduced by Yule in 1921 to explain the relationship between mortality rates and number of marriages conducted by the Church of England. It is familiar to you from your, even though these variables are not related, R was equal to plus 0.95. So spurious regression problem is there. The second one is, problem is, suppose that we regress y on x. The third variable z is also there. R square may be high because x and z are correlated, but not included in the model. You may get a high correlation between y and x. Actually, it may be the impact of a third variable z. Such a possibility is there. The third one, as we have stated earlier, correlation does not imply causality. Our idea of causality must come from outside econometrics. It must come from theory. Even if there is correlation, that does not mean that y is the cause, y is the effect and x is the cause. Then, when distinction is always made between time series and cross-section data. In the time series data, as the same homogeneous unit is sampled again and again, the value of R square will be very high. Whereas in the cross-section data, as the units are heterogeneous, R square will be low comparatively. The fifth problem is, low R square does not mean that our choice of the model or the choice of the explanatory variables is not good. There is no such a interpretation. Also, as we have just stated, to compare two models in terms of R square, y will be same. You cannot compare y with L and y. So there are so many problems associated with the R square. Spurious regression problem, the presence of a third variable is there, need not imply causality, high in time series but low in cross-section data. Low R square does not mean that the model is not good. So there are so many problems associated with R square. So when one use R square as a measure of goodness of it, as a criteria for model selection, one must always keep this in mind. Remember this, in econometrics, our aim is not to fit sample regression line to sample data. Our aim is to use the samples to make inferences about parameters. So our concern is the coefficient, how the size of the coefficient, the sign of the coefficient, and its significance. If in this process the value of R square is high, it is good and well. If it is not low, if it is low, it does not mean that the model is bad. Remember this always. And also remember that R square is nothing but the square of the correlation coefficient. Correlation between y and y hat. So another interpretation of R square is, it is the square of the correlation between y and y hat. That is the correlation between actual y and the points lying on the sample regression line. That is all about r square and r bar square.